maths and then going on to steel. That's a fair old challenge, I think. You may wonder why steel's here on an innovation day, and I particularly picked the theme of materials for the 21st century. You probably think steel is just that kind of greyish stuff that goes rusty now and again. But in 15 minutes, I hope to convince you to be as enthusiastic and passionate about steel as I am. It is a wonder material, actually. It's composed of one of our most abundant elements. It's at the heart of our sun and solar system and the very core of our planet. It is a wonder material of the 21st century, but in fact, every century. It touches all of our lives, all of the time, and in this post-carbon world of the 21st century industrial revolution, everything you or I touch or use is either made of steel or made with steel. In fact, if I had a bit more time, I'd ask you just to look around you as you sit there and reflect on that thought. Just a quick bit about Tata Group, now that I've got your attention. Tata Steel is part of the Tata Group of companies, almost 100 companies, big and small, united by a common code to use our efforts and success to contribute back to society. 2/3 of group level profits are held by charitable trusts for that purpose. We cover everything from fibre optic undersea communications, financial services, vehicles, other engineering products, materials, tea, coffee, water, salt, through to watches and luxury hotels. The vision for 2025 is for our products and services to directly touch 25% of the world's population, something that steel is already doing. And we are very serious about innovation in the organisation. We run a range of innovation schemes, including Innovista, where all of the Tata companies compete across various categories of ideas development. And we even have the category of Dare to Try, so that we can celebrate those ideas that haven't yet been successful. I wanted just to also reflect on steel as a wonder material. It goes back a long time. 3000 BC was the first archaeological evidence of primitive smelting facilities. And in the bloomeries of the Middle Ages, we were producing around about 1 kilogram of smelted iron. But actually, in the Middle Ages, when those samurai swordsmiths were kind of developing the art of producing swords, they actually knew a thing or two about nanotechnology without realizing it. They were able to combine low-carbon, softer steel types with a lot of beating and folding to manipulate the structure. And they knew that higher carbon-based steels were harder and would retain a sharp edge. And they managed to sandwich this together to produce a strong central part of the sword and a very sharp edge. And in fact, the Damascus steels and the patterns that you see on them actually represent this kind of process of beating, shaping, and forming the blades, and they even contain carbon nanotubes. As we move through the centuries, we find that steel has been an enabler for the last 200 years of the Industrial Revolution, and has been innovating ever faster ever since. And so those alchemists from the early days of steelmaking were really just the nanotechnologists ahead of their time. There are some unique properties of iron that lends itself to being a wonder material and lends itself to be part of nanotechnology. Steel is in fact an alloy of iron and carbon, and the phase diagram shows that iron in cooling from molten at 1536 degrees C passes through a number of structural phases. These have different atomic arrangements and different atomic densities. And these phases can hold different proportions of alloying elements, such as carbon, and that there are various material volume changes. And if we combine all of this complexity, we know that we can modify the structure of steel, and we can develop different properties for steel in many, many different ways. And the precipitation, for example, of nanoparticles such as niobium carbon nitrides results in a wide range of microcrystalline structures, both singly and in combination. And depending on the processes, we can then give a wide range of bulk material properties from strength, toughness, and formability. It's a very complex arrangement that gives a massive opportunity for our metallurgists to push the boundaries of the art of the possible, a sort of great material bake-off, if you like. And of course, we can shape steel in many different ways. Once we've got chemistries arranged post-casting, we can apply a bit more magic by controlling the rolling, the cooling, and the reheating at different rates to allow the manufacturer to tailor the properties for any conceivable application. Process lines have complex arrangements of facilities to enable precise control of temperature and shape. And innovations here lie not just in the steel chemistry itself, but in the technologies that allow us to precisely control the temperature and deformation. Just remember that in strip rolling, we're probably rolling a sample piece of around 5 tons, but at 500 meters per minute. So precision and control of the manufacturing is absolutely key. And of course, we supply into a wide range of sectors. And that means we can tailor our materials for those different sectors. They might take into account strength, toughness, formability, creep resistance, wear resistance, weldability, and many other specific parameters, often for some of the most harsh applications, whether it be extremes of temperature, impact, vibration, chemical attack. And not only this, but steel is having to do its job day in and day out. We literally put our lives in the hands of steel metallurgists. They might be holding up the ceilings and the floors of our buildings. They might be preserving our food, generating our power, or ensuring that we can travel in comfort and safety. And furthermore, we've developed many ways to combine our steel with the best of other materials to deliver hybrid solutions in ever more demanding applications. And on the right-hand side on the picture there, you see even things such as the Large Hadron Collider and Space Station have got steel as significant components. So if I take a brief look at how steels have transformed the performance of our personal transport, the car. 50 years ago, the car design engineers had just 2 grades of steel to choose from, mild steel and high-strength low-alloy steels. But today, every part of the body structure has an application-specific material, advanced high-strength steels to provide the correct weight optimization, combination of strength and stiffness, ultra-high-strength boron-bearing steels to protect the passenger cell from collapse, and steels with high strain rate sensitivity that actually absorb more energy the faster the impact in a crash event. And not forgetting that high surface quality finish and formable steels that we need to produce the beautiful car bodies that we actually see today. And corrosion is a thing of the past, unless perhaps you might have had a Fiat Strada back in the 1980s. But we've progressed through zinc-based hot-dip galvanized coatings to some of our more recent magnesium and zinc offerings, a product called MagiZinc, which provide lower coating weights and higher corrosion resistance and surface quality, and the sort of things that we actually now take for granted. It is not just the vehicles themselves, but we work with vehicles and highway designers to understand and improve barriers on motorways and bridges to catch errant vehicles and to minimize the injury to occupants and danger to other road users. Much of our innovation is in partnership with both academia and industry. We've more than 50 collaborative developments in place today in the UK, ranging from SME technology developers to blue chip PLCs, helping them all to benefit from optimized development and the application of steel's potential. We're looking at ways to help bridge the industrialization valley of death. I think I heard that mentioned a little earlier in the mid-range of technology readiness levels. Climate change challenge for the automotive industry means that in 20 years' time, pretty much every light vehicle we'll be driving will contain an electric motor. It might still contain an internal combustion engine, but electric motors will feature much more highly in the vehicle. And the electric powertrain of vehicles is an area of challenge and opportunity. Non-grain-oriented electrical steels provide the rotor and stator materials for our motors, and specialty gears, bearings and shaft steels provide the transmission materials. You see, these days, the electrical steels don't just have to have electrical properties, but they have to have guaranteed levels of mechanical performance and a level of steel cleanliness to deliver lightweight solutions and a much increased and smaller, lighter and reliable powertrains. Developing these with both large and small industrial partners requires a new way of us thinking. And so working with small volumes and with designers and development, we have to move swiftly up into higher volume as demand grows. And so as part of that concept, we developed an idea called the Proving Factory, which was developed in partnership with a company called Productive, a new generation of Tier 1 integrators. And Tata Steel provides the machined components for assembly by Productive, working with a range of small technology developers until such time as demand approaches normal automotive levels of volume. And we also see that as things actually develop, our long-served methods of casting and rolling start to look unsuitable in certain applications. And so a big focus for us is to develop research in powder metallurgy, where we have significant collaborative projects to develop net shape processes for high-grade specialty alloys for aerospace and energy and power applications. There's actually massive scope to develop and use steel in a more functional form. And here we see in the built environment, the scope for innovation is tremendous, with a wide portfolio of beautiful and functional products, as well as providing structural steelwork to support the fabric of the building. We're working closely with architects and consulting engineers to deliver specific required solutions. The beauty is obvious, but the functionality comes with the ease of construction, with properties such as self-cleaning surfaces, with heat capture, with electricity generation, buildings that actually act as power stations, and with long life. So if you just take a look at some of these examples on the screen, we use a product called Colour Coat Prisma, which is an outstanding paint system used to clad buildings. We've developed products that contain a field composite insulating panels to reduce energy costs. In the Paradise Square example and the Sports Hub in Singapore, we're making extensive use of a specially produced Celsius round and elliptical tubular sections, which give a bright and open space and long span capability, and in this case also a moving roof. And in the Burj Khalifa, a specially shaped and designed composite steel floor system called Confloor gives minimal floor thicknesses and wide free spans to enable more floors and less in the way of intrusive supports. The not-so-humble tin can protects our food and drink. It's been a tremendous innovation in thin-walled material and manufacturing technology. Steel cleanliness, bringing us back to the nanotechnology piece again, and surface quality is critical here, as can wall thicknesses are often less than 0.1 of a millimetre, and so any imperfections in the steel would cause a tear. But more than just the steel, there are innovations in the coatings. They include antibacterial coatings on the inside. And our latest in-house development on coatings, known as Protact, is both cost-effective and fully compliant with legal requirements. And it is hugely important in preventing the 90% of food waste in the field-to-table supply chains in developing countries. So please just note here that while I represent a steel company, we are more than just metallurgists. We employ experts in polymer chemistry, surface science and engineering, and measuring systems, to name a few. And equally, as we will hear shortly, some of this also includes use of graphene as a new source of coating. I mentioned earlier about coating developments in the automotive sector, but there are other even more functional applications that we are working towards. The current generation of hydrogen fuel cells for electrical energy generation are still far too expensive for volume application. And graphene is an exciting material that we will hear about shortly, but the research has not yet found routes to the high volume cost-effective products. Low carbon steels can provide a suitable substrate for high volume applications, and the know-how that is developed should enable us to differentiate our products and to give a much more sustainable steel industry for Europe, which I believe is also vitally important. And since I'm on the topic of sustainability, it's also worth thinking about how steel is used in the life cycle. Most more raw materials and their refined products are high energy intensive at the production stage. It is therefore vital that material makers keep a focus on this circular economy. In construction, steel is significantly more recyclable than concrete or wood. In fact, if you look at some of the other components here, wood and concrete are mainly downcycled rather than recycled. And even in the automotive world, if you take a full life cycle analysis, the in-use phase of the life cycle is gradually reducing, but the manufacturing and end-of-life phases are becoming increasingly important. And if we take the application of advanced high-strength steels to give us further lightweight potential in vehicles, that further adds to the steel's life cycle analysis credentials. And this Picture here just shows how steel can be so much better than aluminium and carbon fibre. I've given a few examples of how steel research and innovation is addressing the future needs of society, but there are many areas of future challenge that we need to find solutions for. We know that steel can address the issues of CO2, electric vehicle design, cities big and beautiful. We heard that comment this morning, actually. There's more people will be living in urban environments. And also, I believe it's able to contribute towards reducing waste. Just think of food packaging and pollution. So lightweighting and canned products are a very important part of this. And looking at how the megatrends impact on steel and steelmaking is vital for our future scoping. And we need to leave no stone unturned in this quest. This is, after all, an innovation summit. And so here I ask for your help. Because we've actually recognised the power of innovation can come from many directions. There's no reason why we at Tata Steel would have all the answers. And so to address this, we've set up a Tata Steel Open Innovation Portal. Anyone can log on to this site and they can register their ideas. And we've placed a number of challenges on that portal that we see are important for the future. For example, how can we use coatings on steel strip to improve the magnetic properties of steel for transformers? What steel solutions can handle the transport of sour oil and gas? And we heard this morning about the potential of the hydrogen economy. We'd look at suggesting designs and technologies for piles for offshore structures. How to have better pre-painted steels for the building envelope with enormous scope for buildings to actually generate energy. And how steel could be used to give more precise and more detailed parts and part design. There are an enormous number of examples of these, and we will continue to work forward on taking these technologies in order to improve our business. Thank you for listening. I hope that some of this enthusiasm has rubbed off on you, and I think perhaps I'll hand over now to James, who will pick up on the graphing aspects.